Hi, everyone. We'll get started. So I don't think I have too many announcements this week. We have just an exam on, or not an exam, a quiz on Monday covering unit 6, which is thermodynamics. I think that's been like the past 3 weeks in lecture, or weeks 11, 12, 13. So that's just coming up on Monday, and then everyone should have their exam 2 grades by now. And the answer key should be posted for that as well. And then I think that's it. I think that's all I have. Any questions for me about class or things in general? All right, any questions for me on content, things we want to go over, things we're confused about? We just want to see some practice from what we're doing in class recently. Yeah, okay. Let's try this one. All right, so we have used the delta HF values below to calculate the delta H naught for the following reaction. So we have N2H4 and water forming ammonia, NH3, and oxygen, O2. And we're given your standard enthalpy of formations. How are you going to go about solving this type of problem?
You would just add the ones for the product and then the ones for the reactant and subtract them.
Perfect, right? So we're looking at the sum of the delta H's of the products minus the sum of the delta H naught of the reactants. Okay. Is there anything else we need to do for this problem? So then why don't you take a second to finish copying if you're still copying, or solve the problem. You can work with whoever's around you, consult. I'll solve it myself, and we can agree or disagree on the answer. Okay, so what are we plugging in for our product side of this? Say it again. Yep, so we have our NH3, which is ammonia. And that would be, NH3 is 46.19. Do we need to multiply that by anything? So, right, always make sure that your reaction is balanced before you start doing these, because the molar ratio of your reactants to products is going to matter here. So based off of nitrogen, right, you have N2 and N here. We want a 2 in front of NH3. We need, right, and then that balances, that makes 6 hydrogens, that then balances the hydrogens on the left, but we have 2 oxygens on the right, so this is going to put in 2 in front of there, therefore screwing up our hydrogens. So then I would put a 2 in front of N2H4 and a 4 in front of NH3 to make that a balanced equation. Okay, so what are we multiplying 46.19 by? Now we need 4, right? We need 4 of those. Okay, so that's the sum of our products. Do we care about the O2? Nope, that's in its elemental state. Any of your diatomic atoms, those in your elemental state will always be 0. That's because it exists like that. We don't need to change it in any form. So that's our products, and that's going to be subtracted from, what are we doing for N2H4?
How do you know that's your product if it's a double arrow?
Just looking at left to right, you can say
Okay.
that it's gonna be the products. Most of the time, or probably what you'll see is just a forward arrow, but you can just read it as products on the right, reactants on the left. Yep.
Thank you.
So what are you doing for N2H4 as a reactant? So then we'll take 2 times 95.4. And then which value for the H2O are we using? Does it matter? It does matter, right? The state of your element or the state of your compound is going to change its enthalpy of formation. So do we want to use the liquid or the gas one? We want to use the liquid, right? The liquid is given to us in our problem. So then we'll do 2 times negative 285.83. Oh, so what do we get for our delta H of formation? And then what are the units on that? Okay, so it's actually just going to be kilojoules. You'll have a multiple choice question, so you won't need to really know them unless they're changing the units per question or per answer choice. But the 4, the 2, those are all of your molar ratios, right? So you're saying I have 4 moles of my ammonia. So when we plug in 46.19, this technically has a kilojoule per mole unit as you're plugging it into the equation. So that 4 moles times its heat of formation means that we have, right, just kilojoules left over for those units. So you do only end up with kilojoules as units at the end. Is this an endothermic or an exothermic reaction? This is an endothermic reaction. What does the world prefer? Does it prefer endo or exothermic reactions? It prefers exothermic reactions. It releases heat, and releasing of heat will also contribute to the entropy of the system. And if you can increase the heat, you increase the disorder most of the time. But that just, if you're releasing heat, then you're allowing for other reactions to happen using that heat that is released. Any other questions on this type of problem? Does this make sense? So the O2, this is going to be in its elemental state. And anytime you have an compound or an element in its elemental state, then it has a heat of formation of 0, right? What the heat of formation tells you, the 46.19 is saying that in order to make NH3, this much heat is released when that happens, right? In a separate reaction. But oxygen exists as oxygen, as O2. So we don't need to do anything to O2 to make it look like that. It just exists like that. So we don't need to put in any energy, but to make NH3, that doesn't naturally occur. Something needs to happen. Yep. So, right, if you see N2 gas or H2 gas or F2, what else exists? O2, Cl2, bromine liquid, and I believe those are the correct states. Right, but all of your diatomic elements, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. If you see those in a reaction, those will all have a heat of formation of 0. Another good indicator that it's 0 is that if it's not given to you in the chart or in the question, that's probably assumed that it's 0 and we just didn't give it to you. So since that was not in your list of enthalpies of formation, you probably don't need to use it. Any other questions there? Okay, and then you could also work backwards, right? If I gave you that the heat of formation was 1.96 and I asked you for the heat of formation of ammonia, right? Then that would mean you have the same equation, but now this component here, this would be your x, right? So you're just solving for x that way. So you can go backwards to find a heat of formation if you're given everything else. Yep, endothermic because it's positive, right? Anything with a positive delta H is endothermic. Okay, any other questions? What does delta S mean?
Entropy.
This is your entropy, and what does that mean? What does that refer to?
Energy dispersed. Or
Is it like how dispersed the particles are, right?
Yep, so
Or is that not?
kind of, it's on the right track.
is it disorder?
It's disorder. Yep, this refers to disorder of something. Right, so something like a solid, like this desk, is very ordered, right? It has its shape, it maintains its shape, it has structure to it. So solids have no disorder. Well, they have some disorder, but right, they have a very little bit of disorder. Those molecules that make up a desk, that make up ourselves, right, that make up the desk you're using, they're all small molecules that are actually vibrating a little bit, but that's all they can do. They can only vibrate.
Is it right to say that like more random something is?
Correct.
More entropy?
Has more entropy. Yep, right. So
Okay.
if your room's a mess, that's actually contributing to the disorder of the universe.
Right.
That's actually good.
Okay. But if something had like more particles, but was less, like random,
Mhm.
but something that had less particles, would it still be a lower entropy?
It would have to depend on either concentration or state of the thing. We
Okay.
can do an example of that in a second.
Okay.
Right, so right, we have solids, liquids, and gases. Your gases are going to be your most disordered. Right, and this is just your middle. Because liquids still have some of those intermolecular forces in between the compounds or in between the molecules. It's when we get to that gaseous phase where we're breaking those intermolecular forces and we're just left with individual particles that can bounce around, right? Gases are constantly moving. You can heat them up, whatever. If you think about a pot of boiling water, when it first is letting you heat up, right? Your water is stagnant. As you start to boil and add heat to it, they're getting more disordered. You see more bubbles. The more heat you add to it, the more bubbles, the more disordered that water gets. So gases are going to be your most disordered, and the transition from liquid to gas is much greater than the transition from solid to liquid. I'll give it 3, right? If you change the state from something liquid to gas, it doesn't matter really how many particles you're either adding or subtracting. That phase change of going from a liquid to a gas is more contributing to disorder than particles. So if you have 2 particles going to 4, or you have 1 particle that's in the liquids phase going to one particle at the gaseous phase, right? These are both liquid. 2 particles going to 4 particles in the liquid phase is going to have less disorder than that 1 particle going through a phase change, right? That 1 particle getting to the gaseous phase now has more disorder than any of those 4 liquid particles might have. Okay, does that make sense for your question?
Yes, that makes sense.
Yep. All right, but if we have something where we have 2 molar NaCl and we have 1.5 molar barium hydroxide. Which one here has more disorder in solution? Why do you say the 2 molar?
I just remember back in class, like, there's more moles in it.
So, great thought. Right, what does sodium chloride do in solution? What kind of compound is sodium chloride? Is that ionic, molecular, something else? Covalent? It's an ionic compound, right? It has a metal and a non-metal. So what does that do in solution? Does that stay together? Does it break apart? It breaks apart, so we form Na plus and Cl minus. So that means in solution, your 2 molar calcium chloride or sodium chloride now turns into 2 moles of sodium ions and 2 moles of chlorine ions, making us have 4 moles, right, of those ions in solution, right? If we add those up, we get 4 molar total. What about barium hydroxide? What does that do? Does that stay together or does that dissociate? Does anyone recognize what barium hydroxide is? If you think of acids and bases, is this one that rings a bell? So this is one of your strong bases. So this will also dissociate. What is this going to dissociate into? You have barium 2 plus and what? We have OH minus. How many OH minuses do we have? We have 2. So what's our concentration or what's our molarity of the barium 2 plus once that dissociates? Close. That's going to be for the that's going to be for the OH minus, right? For barium, we have a 1-to-1 ratio of barium hydroxide to barium ions. So this turns into 1.5 molar. But what's our ratio of barium hydroxide to hydroxide? 1 to 2. So what does that mean for our concentration? We're doubling it, right? So this turns into 3 molar for our concentration of hydroxide ions. So what's our total concentration? 4.5. So now go back to your statement. Which one has more concentration or which one has more molarity? Sodium chloride or barium hydroxide? Barium hydroxide has overall more molarity. So which one has more disorder? Barium hydroxide will be more disordered or have more entropy than your sodium chloride solution, because we have more concentration of ions in our solution at the end.
That was an average of the two molarities of barium and, or is that just like what it was already given?
It was already given.
Okay.
Yep,
And then the 3 is all of the molarity of the right side?
the 3 is all the molarity of the OH minus, right? So if we said I have 1.5 molar barium hydroxide, right, for every 1 mole of barium hydroxide, how many moles of OH minus do I have? You have 2, right? Because we have 1, 1, 2. So we have 2 moles of OH minus, which means that our concentration of OH minus is, sorry, this should be, oh no, that's right, is 2 molar, sorry, 3 molar OH minus. That means we have this many concentration, or like this concentration of OH minus in solution. If we did the same thing for barium, we would see that we have 1.5 molar barium ions. So the total is 1.5 plus 3 to say 4.5, if you want to look at it that way.
Could you tell that by seeing that it has more bonds, or you still have to calculate? Like, could you tell something is more disordered because it has more bonds?
Probably. I'm trying to think of a couple examples to see if I can think of an or a big
An exception.
exception to that. I think that would be correct.
But still check.
But I would still check, right? You can do that, and that would be like a good idea to say, I think this one's gonna be more disordered. Let me check the math to make sure, kind of thing. I can't think of an example where it wouldn't. So I'm gonna say probably. Okay. Any questions on entropy and how we determine differences in entropy? If something is, if you have 2 of the same substances, or I guess not, you would have 2 of the same. If you have 2 things that are equal molarity and one is heavier than the other, which one would have more entropy, the light thing or the slow or the heavier thing? Why do you say the light?
Control letter.
Yep. So, right, if you're looking at something that's light, think of a small kid, that's going to run a lot faster than like a big dude, right? Someone that's small and has not a lot of stuff to them is like a 6'5" guy that's jacked, right? He's going to run slower than the little kid. They can move around and go into other places. That big 6'5" guy has to squeeze through things, right? So he's going to have a harder time moving. So that heavier molecule will have a harder time being a gas and bouncing back and forth across the walls. So something like H2 gas, right, will be very disordered because that can move very quickly. It's very light. Where something like xenon gas, right, a noble gas that's very heavy, that will be a little bit less disordered because it's pretty heavy and it doesn't move around as quickly. Okay, so your lighter elements or your lighter compounds will have more disorder than your heavier stuff. Okay. You can do the same thing that we did for the first question with your delta H of formation with delta S. The thing you have to remember with delta S is that it will always be positive in terms of the entropy of formation, because right at 0 Kelvin, that is when delta S is equal to 0. Anything above 0 Kelvin will put some disorder into the system. Because anything with a little bit of heat will then cause your molecules to vibrate, which then gives disorder to the system. Okay, what does what does the world prefer? If a delta S is increasing disorder, what kind of sign does that get? Is that a positive or negative delta S? This is a positive delta S. And if we're decreasing disorder, what does that mean? That's a negative delta S. And what does the universe prefer?
That's disorder.
We actually prefer more disorder, right? So we do prefer a positive delta S.
They want, like, cause if, 0 Kelvin is the least amount of disorder we can get to, and like 0 Kelvin's like impossible to get to, but in a lot of researchers, they like do their best to get there, so there's like less.
Yes, right. There's less factors going on, right? The colder it gets because we don't have disorder to deal with it. Right, but this has to deal with like degrees of freedom and how much your molecules are moving and stuff. So people try to either model this as best as they can to try and decrease entropy, and just look at what's actually happening or whatever. Or sometimes they're trying to create more disorder and see if they can get a more disordered reaction that then can then be used for something else later on. So let's look at an example. Okay, so we have N2 gas and H2 gas going to NH3 gas. We need to balance this equation. So how are we going to balance this one? Right, so we have 1 mole of N2 gas and 3 moles of H2 gas forming 2 moles of NH3 gas. So what do we think is going to be the delta H and delta S? Kind of gave you a hint for delta H. Couple questions ago. Or you know what delta H is actually from a couple questions ago.
0?
It's not 0. Why do you say the S is negative? Perfect, right? So before our reaction, right, in our reactants, we have 4 gaseous particles, right? You have 1 N2, and then we have 3 H2. And then at the end, we're forming 2 NH3 molecules, right? So we're going from 4 molecules to 2. 4 to 2 is a decrease in particles, which is a decrease in disorder, right? They're all at the gaseous phase. We can just look at particles as 1 to 1 to 1. So delta S is going to be negative. What about delta H? I did tell you what delta H was. I told you that delta H was negative, what, 94 point something? 46.19. Okay, so this would be, I did tell you that delta H is a negative. How you would predict this is just based off of how many bonds are being broken, and which bonds are being formed. You can solve for delta H from the bond enthalpies. So, right, you have an N triple bond from your nitrogen, and you have an H single bond from your hydrogens. And you're forming two ammonia compounds.
How come you didn't multiply by two? If there's two,
So I just drew two NH3s. I don't need to.
but in the delta H,
So that's like the delta H I gave you. So in our question above, right, I gave you NH3 and I told you that the formation of NH3 was negative 46.19. So, right, we know it's negative even if I multiplied it by 2, it's just still negative, right? Right now we're just caring about if it's negative or positive.
okay.
Yeah. Right, so this would be a negative one. When we're looking at what's being broken, we have we have a triple bond being broken and 3 single bonds. And then 6 single bonds are being formed as we form NH3, right? We need to make all of these individual and then we need to reattach them. These all have an energy associated with them. So, right, NH3 or N triple bond could be, I don't know, 300. And then H single bond would be 400. I'm sorry, 100. But then your NH3 would be, I don't know, 250. What's that call it? Right, so the energies for all of these bonds are below. We'll call this. Right, so this is 200, 100, and 250. If I just made up those numbers. If we want to look at the energies of these bonds, we can do the same thing that we did for the delta H formation, except when we look at bond enthalpies, instead of doing products minus reactants, we're going to be doing bonds broken minus bonds formed. Where do we break bonds? On the reactant side or the product side? Where do bonds get broken?
Yeah.
Reactants get broken. So this is reactants. Where do they get formed? On the products. Yep. So instead of this being products minus reactants, for bond enthalpies, looking at the strength of the bonds between molecules, we now have reactants minus products. Okay, so for those types of questions, you want to be able to write out the structure and say, okay, how many bonds are being broken? How many bonds are being formed? And then what type of bonds are being broken and formed? It would be another chart type of question, but just be on the lookout for those as well.
So that's how we always have to find entropy.
This is for still enthalpy. So this is still talking about delta H. This is all for delta H.
Okay.
Delta S is the same thing like the first question we did. It would give you delta S of formation of the molecules in that way.
Oh, and then we just do product.
Yep, and that's still products minus reactants. Yep, the only time you're doing reactants minus products is in this case where you're looking at the actual bonds of the molecules. How far did y'all get in class today? Did you finish week 13?
We didn't get to do Gibbs.
Gibbs, okay, that's what you're doing on Friday. Okay, perfect. Cool. Any questions on delta H or delta S? They're not too bad. Okay, so then just a little bit more with delta S. We just need to remember that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. Okay. The system for delta S is usually going to be the reaction.
This is by you.
Everything else, right? So you have, if we look at the universe, we could have, or if you look at delta S, right, you can have me as the system, this room is the surroundings, the universe is everything else beyond us, right? So it's like system is the immediate thing, surroundings is the immediate stuff around it, universe is everything else. Okay, so that's going to be for the reaction. This is your delta S, not a formation. So similar to the first question that we did, but this time just using delta S's. Still products minus reactants. What about the delta S of the surroundings? Does anyone remember from class what we called that or how we defined that one? If it was at constant pressure. What does delta S of the surroundings turn into? That will equal Q of the surroundings divided by temperature. But at constant pressure, this means that the Q of the surroundings is equal to the negative Q of the system divided by temperature. Right, constant pressure, think of like a calorimeter or just your usual calorimetry of a metal being dropped into a pot of water kind of thing. Does anyone remember what we say delta or what Q of the system, negative Q of the system is equal to? So it's negative delta H of the system divided by T. So if you know what the delta H of the reaction is, right, you can use that version to get the delta S of the surroundings. You can use that delta H to get the delta S of the surroundings. Okay. Right, and then we know that if delta S of the universe is greater than 0, then this will be a spontaneous reaction. Only when delta S of the universe is greater than 0 will we have a spontaneous reaction. Okay, any questions there? And I think the only thing I didn't go over today is Hess's law. Do we feel comfortable with Hess's law or just want a quick review of that as well? Review it? Absolutely. Any other questions on delta H or delta S before we move on? Okay. So then, quick review of Hess's law. This one is like one giant puzzle, and this is like the sum of the parts will equal the whole. So if you have a reaction, it looks like this. And we have our overall react, and we'll say the delta H. And we know that our overall reaction is A plus 2B goes to C. But I don't know what my delta H for this is. We can use the broken up steps in order to find what the delta H of the total would be. Because delta H is a stepwise function, right? It doesn't matter on the path. So how do I need to manipulate my equations in order to get from our two-step equation to our overall reaction? I don't need to do anything, right? If I were to sum my two reactions, I would get A plus 2B plus D goes to D plus C. The D on the left and the right can cancel out. So my A plus 2B goes to C. If that matches my overall reaction, what can I do to my delta H's? You can just add them. So I can take negative 250 plus 150, and I get negative 100 as my delta H. Any questions on this here, this example? All right, so what if I gave you the same overall reaction, right? We're still looking for A plus 2B goes to C, but now the equations I gave you right, now I gave you those delta H's and these equations. What do I need to do in order to get to my A plus 2B goes to C overall equation? Yep, so you need to multiply 2 by -1, or you need to flip your reaction, right? I don't want C as my reactant, I need C as my product. So I'm going to flip this guy. So I end up with D plus B goes to C. So what does that do for delta H2? Negative. So this now becomes negative 450. Right, we don't care about this guy anymore. Then I could add up my purple equation and my blue equation. And now this time, delta H would equal a negative 150. Okay, if this was the problem we were solving. What happens if I multiply, or I have to like multiply my whole thing by 2? Well, you multiply your delta H by 2, right, as well. So if you're tripling things, you have to multiply your delta H by 3. If you're dividing, you have to divide, right? It's the same operation that you're doing to your equation that you're doing to your delta H. Thank you. Any questions on the second example? Do you want to see an actual example? Yeah, okay. Okay, so we have calculated the delta H for the following. We have 2C plus H2 gas goes to C2H2 gas. Okay, so what do we need to do? What jumps out first? Does everything look like it's supposed to?
Which equation would be-
The first one?
This is the. Oh, the third, or the second.
The second one, right? So we see that we have 2C2 or 2C in our overall equation, but we only have 1 in our second equation. So we're going to multiply this whole thing by 2. So I always like to rewrite that. And then that means that delta H naught will be the negative 787.0. Okay, what else needs to happen? Okay, so if we flipped, I'm okay with flipping it. If we multiply by 5, what does that do to our? Right, so then there's too many H2Os. So let's look at our, let's look at our overall equation. If we're moving from left to right, we fixed the 2C. What about our H2? Where do we see H2 in our 3 equations?
On the product side?
Just the H2? Right, so H2, is that a reactant or product in the overall? It's on the reactant. Where in our 3 equations do we see the H2? What equation? Third one on the reactant. Does it match our overall equation? It does, right? Do we see it anyplace else in any of the other reactions? No, right? So since this already matches from our overall equation, we don't want to touch the third equation, right? We're going to use it exactly as is because there's no other place that H2 exists. So if we manipulate the third equation, then we're changing our overall equation. We don't want to do that. So we're going to keep the third equation as is. Right, so then we move to our product of C2H2. Where do we see that in our 3 equations? The first one, is it on the side that it's supposed to be on? No, it's not, right? So what do we need to do to the first equation? We need to flip this one. So this now becomes 2CO2 and H2O liquid forming C2H2 and 5 halves oxygen. Bless you. Bless you. Okay, so then this delta H now becomes positive 1299.5. Do we have anything else that we need to manipulate? I'll give you a hint. Did you manipulate all of your equations to match your overall reaction? Yes, right? We did our C2, or we did our 2C, we did our H2, and we changed our equation to C2H2. So if we have our overall equation and all of those things that only appear in one equation look correct, everything else will fall into place. And if we look at that, right, if we look at these equations here, right, these are the three that we're going to be using. Your H2, H2O is going to cancel out because that's on opposite sides of the equation. Your CO2 are going to cancel out because those are on opposite sides of the equation or on the arrow side. 4/2 can actually be written as, or 2 can actually be written as 4/2. So if you added 4/2 to 1/2, what do you get? You get 5/2. Does that match the 5/2? It does, right? So these will match up. So since they all have something on opposite sides of your arrow, those will all cancel out. So you're just left with 2C plus H2 forming C2H2. So what can we do to our delta H's? We can just add them up. So we'll have -285.5, -787.0, and 1299.5. And we end up with 226.7. Okay, does that make sense as like an actual example? That one's a little tricky with the 5/2, but I don't think we'll throw that on you. It's good to see it as a practice. Okay, feeling okay about this stuff? Any other questions on the material? All right, so I think the only thing left to cover before your quiz is just delta G. So you do that on Friday and then you should be good to go. All right, cool. We'll call it good for today then. If there's no other questions, if you do have questions, just feel free to ask me. And if not, have a great rest of your evening. Thanks for coming.